The broadcast is now starting. All attendees are in listen-only mode.
All right. Good morning, everyone. We are about 1 minute from 10 o'clock. We'll give people another minute or 30 seconds or so to jump on, and then we will get started. All right. We are just after 10 o'clock, so we'll get started. Welcome, everyone, to the Hartfiel hosted webinar. Today, we are going to be talking about robot guidance, the robot guidance portfolio from SICK. We've got a couple of cool products here today, so we will just jump right in. So, quick introduction to myself. My name is Josh Sparrow. I am the Sensor, Vision, and Safety Product Manager at Hartfiel Automation. I deal with the SICK product line every day. Here to support you guys. We've also got Nick Longworth. I will let Nick introduce himself.
Hi, everyone. Yeah, I'm Nick Longworth. I've been with SICK for about 6 years. The entire 6 years I've been functioning with our robotics products, whether it's robot guidance, safety, general sensing technology, really anything. My focus is generally going to be business development for robotics products. Prior to SICK, I was with an end user for about 10 years, being a internal integrator for assembly, machine tending, and welding robotic systems. So been around the block a few times in terms of the technical needs for implementation and the technology involved in robotics projects.
Awesome. So then just to quickly introduce the two companies, for those of you who are not as familiar with Hartfiel, we are a high-tech automation distributor. We've been around for over 65 years, headquartered out of Minneapolis. You can see our footprint here. We've got offices in all of the yellow dots there and cover all of the red states. So we have a number of account managers within those areas. And then people like myself being a specialist for each of our product lines, whether it's SICK or robotics or Mac valves. You can see a sampling of some of our top lines on the right-hand side there. Today, again, we'll be focusing on SICK. But if you guys do have any other questions or any other needs, we'd be more than happy to help out with those as well. And then again, I'll let Nick talk about SICK at a glance here.
Yeah, so for anyone who's unaware of SICK, SICK was started in Germany in the late 1940s by Erwin Zick. His last name is spelled Sick, but Zick in German. And so we've been around for a long time. We started with safety, invented the light curtain, invented the area scanner, right? We're very well known in safety, but we have actually over 40,000 different products and over 12,000 employees worldwide. And we can do a lot more than just safety. So we get into everything from track and trace to robot guidance to safety to just your general everyday sensor technology. Can do a lot of different things in a lot of different industries. So SICK's just been around a long time, and we've been able to do a lot of different stuff within the industry, helping solve applications and pain points.
Awesome. So again, today we are going to talk about the three products, the PLOC2D, which is a 2D vision guided or robot guided solution, the 3D belt pick, which is a simple 3D solution, and then the PLB, which is a much more robust system for robot guidance. Then we'll have a short Q&A at the end. I do ask that if you guys have any questions, feel free to chat them in. We will answer questions at the end, just so we can keep going throughout the presentation. So we're going to start with the PLOC2D. Just a quick description of what the PLOC2D is. This is based on the inspector from SICK, which is a vision sensor. We are running an app on there for robot navigation, but we get the high quality image, the fast speed of those cameras. It's a self-contained camera, so you don't have to have a PLC or a PC or a robot or a vision controller, anything like that. And they've really made it easy to use, user-friendly interface. We'll see that a little bit longer or a little bit later, just how easy that is to use. We also have a couple of different versions. We've got fixed versions, so if you want something that is already calibrated out of the box, we can get you that. Or if you want something that's a little bit more flexible, we can easily calibrate those, but really gives you the flexibility to work with the camera however you guys want. So at a glance here, we are giving you the position of a part in 2D. You can see off to the right hand side, we're giving that location. This is what that software is. We're going to give that position out through the coordinate system of the robot. So giving you actual coordinates out, so you don't have to do a lot of translating or trying to figure out what that is in your robot side. We're going to give you all of the tools to be successful here. All the calibration tools, all of the imaging tools, all of the things that you might need here. And then it's very intuitive and easy. Again, SICK really wants to make things as easy as possible for these robot guidance projects. Getting the robot up and running is a huge task. So being able to make things as simple as possible just makes that process much easier. And then again, standalone sensor. You don't have to have a PC. You don't have to have a vision controller or anything. Everything is self-contained in a unit about the size of your hand. So just some general functionality here. Anyone that's worked on a vision system knows that you can't necessarily tilt things above that 30 to 45 degrees before you start to get a lot of distortion. Or that direct sunlight, shiny parts, things like that. These are things that we can help out with, either Hartfiel or the SICK team. If you guys don't have a whole lot of vision experience, can come out and give some best practices and talk through applications, something that we're more than happy to do. We can also do a fixed mount above, say, a conveyor or above a shaker table, something like that, or we can be robot mounted. Again, we're very flexible in what we're able to do here. We're going to give you out that data in your X, Y, and your rotation. Again, this is a 2D system, so we want to make sure that your parts are always at the same height because we're not really giving you that height out. One thing that's really nice is we do have a match score % here. So if you have a part that is grossly outside of where you want it to be, we can say, hey, we see this part, but it's not quite exactly what you want. So we're not going to pick that for you. Just, again, very simple, kind of easy to tell if you've got bad parts inside of there. Typical performance, you're going to get about half a pixel in the X and Y, and then a 0.1 degree rotation around there. Now, the X and Y accuracy is really going to be dependent on what camera you're using. Higher resolution will get you more accuracy. And then your field of view. So if you're looking at a very large field of view and you're using a smaller camera, we're not going to be able to get a crazy accurate measurement. Versus the other way, if you're using a higher resolution camera with a smaller field of view, we're really going to be able to pick parts that are very small at a very high accuracy. That's, again, something that we're more than happy to work through with you guys when you come and talk to us about this. We've got some field of view charts that will look at different resolutions at different distances. Very simple to set up. Looking at the performance here for the images, typically we're seeing between 0.3 and 1 second to take an image and spit out those results. We want to make sure that we get as fast as possible so we can take one image and locate multiple parts inside of one image. We'll kind of go through that a little bit more in the future slide. But again, we want to make sure that it works for your application and your speeds. So some benefits here. The biggest benefit that we're seeing is, again, that ease of use. You've got a self-contained package. It's easy to set up. You don't have to have previous vision experience. That always helps because you know some of the gotchas that could arise there. But it's as simple as drawing on with a paintbrush or taking a picture of a part, and it'll auto learn some of those. The fast and simple calibration of the Flex versions means that it works for a wide range of applications. If you need to look at a huge field of view, okay, we can figure that out. If you need to look at a small field of view, very simple. And then again, that teach-in, very simple teach-in, both of the part and integration with the robots. SICK actually has sample code written for many of the robots out there so that you can, once you get that connection established, very simply send commands out and receive data back in from the robot. You might have to modify those to fit your applications, but again, we want to make it easy for you guys. And then swift replacement. So things happen with robots. People can hit cameras, robots can come in and smash things, boxes can hit things. Very simple replacement of these to be able to come in, you can focus the camera, and then your program is already loaded and up and running within 15 minutes. So the very simple workflow of this camera is a calibrate the camera. We're going to align to the robot coordinate system, and then we're going to teach the part. Then you're ready to communicate with your robot. We'll dive a little bit deeper in here. So the calibration is coming in, and we can see on the software, we're just going to start from the left-hand side and work our way down. Calibration, we're going to take a sheet of paper, either a A0 all the way up to an A6 sheet of paper. These can be sold, or oftentimes we just print it, put it on a hard backing, something like that, to make it simple. We select what calibration target we're looking at, and then we're going to pass that calibration target throughout the field. What that's going to do is it's going to account for all of your lens distortion. You can see when you get cameras, you get some fish eyes on the outside, you get data that's skewed a little bit. We want to make sure that throughout the entire field of view that your robot is getting accurate measurements. So this is going to basically do that. It is taking 6, 10, 15 images, somewhere in there, and it tells you. You can see there's two little green squares on the bottom of that image over there. That's saying, hey, you might need to come down here and show that calibration curve there. So very visual feedback. It also tells you what the percent coverage is and what that quality is. Gives you your errors that you could see inside of there. The pre-calibrated units already have this done, so you don't necessarily have to do this, but oftentimes, the pre-calibrated versions might not fit your exact application, so we give you the tools to do that. Then we have to align to the robot coordinate system. So we take that calibration square or rectangle, and we align in the software. You can see there's a big align button, and then next to it is a verify button. You put your calibration curve in there, and what this is going to do is it's going to convert your pixels to millimeters so that you actually get a millimeter reading out of here. It's going to flatten. So if we do have to come in at a 30-degree angle, or we're kind of off kilter a little bit, it's going to flatten that image so you get a nice field of view, easy for your robot to work in. We might have to downsample some, and then it's going to take your coordinate system from your robot and align it together. So you do have to load in the coordinate system into your robot through the frame. But again, something that we can walk through. That way, all of your results are aligned to your robot. You don't have to worry about doing any calculations or anything in the robot side. We want to keep that self-contained into here so that all we have to do is spit out the data to you. And then again, alignment targets are available, or we can print them out. Once we're done with that, we teach the part. So you can see over on the right-hand side, we're going to acquire an image, and then we can do a couple of different things. We can brush. So if you've ever taken paintbrush in just like a paint program or something like that, you're going to highlight around the part that you're looking at, and it's going to look for different contrasts, different edges inside of there. You can see we've got kind of this orange glow there. That's the paintbrush. And then our brighter orange on kind of those features there are the edges that it's seeing. So that's what this camera is looking for, is that contrast there. One other thing that we can do for teaching a part is put the part in your field of view, hit the acquire image. An auto button will pop up, and if you hit that, it will say, okay, take the part out of the field of view now. So if you're not confident in brushing around that, this will basically look for any changes between the two pictures that it's taken, one with a part in it and one without, and it'll teach the part based on that. You might have to clean that up a little bit, if you've got a harsh background or something like that, but very simple to set up. Again, you don't even have to be a vision expert. We're also going to be able to program in or brush in your gripper clearance. So if you've got fingers that are 2 inches wide and they're a half an inch thick, we'll account for that here. That makes sure that as you're picking parts, you're not running into other parts or anything like that. We also are going to set up the part reference point here. You can see that there's a green line and a red line and then a circle around that. That's going to be our part reference. Where do you want to pick up the part? So what we're doing is basically setting your offset, again, keeping it internal to the camera rather than having to do all that in the robot. You can do that offset in the robot if you want, just leave it in the center, but we want to make it simple for you. So you're able to come in, you're able to rotate that around. We moved it just a little off center to the left here, so that might be where we're picking up our part. Then we're into operation. We come in and we set it in run mode. If you're communicating with the robot and the robot sends commands to it, it's going to switch to its run mode. The commands are then available to control the camera, and we can locate all of your different parts. We can switch between different jobs. We can look at different ways of organizing the parts to be able to look at, say, a lane of parts and pick from the top to the bottom, left to right. Maybe we want to pick the best scoring part. If you've got a shaker table or something like that, I want to make sure that I'm picking the part that doesn't have any other parts around it so that I can very simply pick it and reliably pick it. We are able to import and export jobs and images through FTP. So if you do have a handful of different parts that you're looking at, it's very simple to switch out between those, or just have those jobs available in case a camera does go down. And then again, your results are available in about that 0.3 to 1 second. So if you do have 3 different parts here, you can see on the right-hand side, we could grab all 3 of those parts from one image. As long as nothing's moving inside of there, we're not on a shaker table that's shaking something or anything, these parts should be there. That gives us more time to be able to take an image and then get more results out of that. Just speed up the process. So a little bit more, multiple parts of the same type, easy. Being able to run multiple jobs at one time. It's a checkbox. All of the parts that I want to be able to look at, I will just train the same way, and then we're able to pick those out of the same image. So this image right here in the middle, we could pick those big ones, we could pick those small ones, both out of the same job and image. That way, again, that speed and that flexibility. A lot of kitting does multiple different parts, or maybe you've got 4 or 5 different parts coming down a conveyor. We want to be able to pick all those without having to know necessarily what's coming down. One other thing that's really nice about the PLOC2D is we can do that conveyor synchronization. Again, a lot of robots might have this ability in there, but you have to make sure that you're doing all the tracking inside of there. You have to tie in everything together. Gets to kind of be a headache. The PLOC2D will actually take care of that internally to the camera. We're going to send the run locate command to the PLOC2D, and it's going to take care of that so that as you're picking those parts, your robot gets all of that data right inside of there. Again, makes it more simple so that you don't necessarily have to stop, take a picture, pick the part, move the conveyor, all of that. Again, want to be as robust as possible in the camera itself to make your guys' job a lot easier once you're plugged into the robot. So just a couple of applications that we've done with the PLOC2D. We've done auto racking, we've done a lot of palletizing, we've done small part picks on a vibratory table. Again, kitting is rather nice, being able to have multiple different parts on one tray makes it simple to set up. So if you have a application where maybe you've got a lot lower contrast or you're coming down a conveyor and you've got a lot of different parts, the next product we'll talk about is the 3D belt pick. And this is taking that conveyor tracking to the next level, being able to pick any height, any different color, any different shape. Because this is a 3D camera, we don't have to worry as much about picking different colors. We don't have to worry about contrast and having maybe a black part on a black belt. We make that as simple as possible. Again, user interface just on a web-based interface. Easy integration. All of these can work with a ABB, a FANUC, a UR, whatever makes the most sense to you guys. And then it's very scalable, very flexible. All of these are pre-calibrated because of the hardware that it is. So you don't have to worry about that calibration step, but being able to have different sizes up to 1.5 meters width of conveyor belt. Very simple, very flexible. So the 3D belt pick as a whole, it is a app that is running for precision detection on conveyor belts. Again, it's going to work with any color, shape, height, so that you don't have to worry about downtime, worrying about, oh, do I have enough contrast? Is my lighting right? Is it a sunny day? Something like that. One thing that's really important about this is you don't have to teach it. We're going to give you the height and a bounding box, so some rotation and orientation, to give you location of anything that's in there. For those of you who work with robot or for vision right now, we're basically using a blob tool, putting a bounding box around that, and then giving you the height. What this means to you guys is that anything that's coming down the belt, we really can pick very simply. Product range, we're looking at either the Tri-Spector, which is the lower end, and then we have the new ruler product that will tie into a vision controller right there. You can see doing the same thing. We're running the belt pick app space app. This extends some functionality, but gives you that simple to use interface. Just some quick features and benefits here. The 3D detection, again, will handle collisions, will handle all that data. We're giving you the height base. So if you have multiple different types of products coming down, or you've got delicate products that you need to know exactly where that top of that is, we're going to give you all that. Simple alignment between the camera and the picking system, easy to use interface. We're going to tie into just about any robot. And then if you need more plugins, if you need something else besides just that belt pick app. We're able to load that in through the AppSpace interface. So we can do deep learning, we can do sorting, we can do all sorts of different things inside of here. So some applications that we've touched on here. We've got the, picking of shrimp, the same product all the time. Very simple. We're just going to give that bounding box, and then you're able to grab those. If you've got secondary packaging or you need that gentle, chips or boxes, things that could collapse, we're going to give you the exact height of the product coming down. Or, palletizing. A lot of times you'll have maybe a couple of different styles of product coming down the belt for palletizing. You want to know what the height of that is without having to reteach multiple different times. So very simple to do. So one thing that I want to mention is that for both the PLOC2D and the 3D belt pick, we don't want to have overlapping parts. The 2D image can't really handle that, and the belt pick is really going to just treat those overlapping parts as one large part. If you do have overlapping parts, that's where Nick is going to talk about the PLB. So I will let Nick run with the PLB here. Yeah.
Thanks, Josh. Yeah, so PLB. This means it's a misnomer these days, but PLB means part localization in bins. It's actually an acronym for that word. And so we made an unfortunate choice about 15 years ago when we released this by calling it that, because today it can do a whole lot more than just bin picking. Today we are getting into applications like depalletizing, as Josh just mentioned, some conveyor picking. We get into form dunnage picking, lots of other applications that have nothing to do with bin picking. So we do call it PLB still, and we try to ignore what that actually means. Now the PLB system is really a combination of hardware and software. What you'll see here is a bit different than what you have with PLOC2D and 3D belt pick, where those are more of like a one-trick pony, right? They do what they do. If it works for you, it works. If it doesn't, that you're gonna have to move on to something else. PLB is a little bit more moldable. It's kind of a combo of hardware and software that can be molded into what you are trying to do for your application. And because of that, it reduces development time for robot part picking systems. It's something that is going to adapt to what you're doing and is going to be able to easily integrate to robot brands and make your life just much easier to solve applications. So a PLB system. This is essentially the architecture that you see here. Now the PLB system itself, the camera, that is just a streaming camera. That camera can be robot mounted or it can be fixed mounted in the workspace. You can see it robot mounted here. That camera is then wired to a industrial PC. That PC can be provided by SICK, it can be, or Hartfiel, or it could be provided by the customer. It's something that we are completely open to somebody providing their own PC, and we can just give specs. But that camera can go to the goes to the PC. The PC is what actually runs the PLB software and processes the image from that streaming camera. You can have multiple cameras to one PC. You can have multiple robots to one PC. There's some caveats to doing that, but it is possible to do that with your architecture. The PC then connects to the robot over TCP/IP socket messaging. Again, as Josh mentioned, for PLOC2D and 3D belt pick, we have several different sample codes for most robot brands to integrate PLB into their controller to pass data back and forth. So the architecture with PLB is very flexible. You can have multi-robot, you can multi-camera, you can have robot mounted, fixed mounted. All those options are out there. The main thing is, what are you trying to do and how do we mold the system to your application accordingly? So you go next slide. So the PLB software we consider as more of a platform than a particular product, right? So the platform of PLB is what we can mold. So PLB is just this core software, and then there's the different modules that get attached to it. And the two main modules that matter are the image acquisition module, that's the camera that you're using, and the other one is the object detection and localization module. That is the algorithm for locating something in the image. We also have hand-eye alignment and communication, which is modular. But those are less important to actually solving the application. They're more about just your needs in terms of that particular application and not actual solution. It's just more configuration needs. So moving forward, the cameras that you get with PLB, these are the different types of cameras that you're going to see. And the cameras are something that is, they're not all the same. They all have a little bit different way of taking images, and you're going to get different performance out of them. So they are tailored to different applications that are targeted by the portfolio. So for instance, the PLB 510 is a lower resolution camera, 3D camera. It has a color 2D image, but it's meant for high-speed applications. So when you're getting into a depalletizing application where you need to use deep learning to deal with, deformed boxes, multi-skew, anything like that, the PLB 510 is a great option because it's going to be high speed. You don't need super high resolution in a depalletizing application. Usually, plus or minus 5 millimeters, perfectly fine. And you're going to get that 300 to 500 millisecond response time that's needed for the application, versus if you were in depalletizing to go with one of the more higher resolution cameras, your cycle time is going to get really pushed up. Your pricing is going to get pushed up. It might not meet your budget or your cycle time needs in that case. Conversely, something like the PLB 520 or PLB 521, those are very high resolution cameras. We use those a lot in, say, automotive applications, where we're picking something like sheet metal stampings that are in a bin, and generally those are going to be large bins, right? 90-inch bins, that kind of stuff that you're getting into, where you need sub-millimeter accuracy when you pick. And we get into CAD matching and some edge matching in those cases. So again, all of these cameras have a different place in the portfolio. The main point for SICK and Hartfield is we're not going to force fit a particular technology into your application. We're going to match your application with what makes sense and what's going to perform the best from a budget and a technical standpoint. So, in addition to the camera, the camera's your eyes. That's how you get your point cloud. It's how you get your 2D image. In addition to those, you have your algorithms. This is how we actually process those images within PLB. You have several different algorithms in PLB. These can all just be flipped back and forth. There's no change to the software, right? So you're not having to change softwares and play with new things every time you change. PLB for the cameras is an abstraction layer. The cameras, the software never changes for them either. Same with the algorithms. You change an algorithm, you might have some different parameters, but the look, feel, and the workflow of the software completely remains the same. The communication with the robot remains completely the same. So your training doesn't disappear just because you changed an algorithm. And so from a solution standpoint, we have all these different ways of solving applications. And so generally, these all, again, have a fit in the portfolio of what applications they're targeted at. For, again, so CAD matching, that's going to be a lot of automotive, machine tending, those type of applications. Geometric matching, we do a lot of that in medical. You get into some foundry and some forging applications with geometric. When I mention geometric, I'm talking about primitive shapes like pipes and surfaces and circles, that kind of stuff. We get into a lot of those for those sort of more basic material applications. Edge matching gets into a lot of delayering applications, like when we get into retail and some other applications like that. And deep learning, you're talking about depalletizing. You might be talking about polybag picking with clear objects. We can get into clear objects. Or you could be dealing with order commissioning, where you're dealing with it could be totes coming in of 700 different types of parts. You can get into that with deep learning and be able to pick those dynamically. So very capable software from its different functions that are built in. So getting a little bit deeper into the deep learning, because this is what everyone always asks about is, okay, you give deep learning, what does that even mean, right? It's the buzzword, it's something that everyone wants to see is AI and deep learning. What does it mean? Because there's actually different types of deep learning out there. Different companies use it differently for different things. The way SICK has gone about this is we believe that for a lot of the traditional applications in 3D guidance, like automotive applications where you have, or machine tending applications where you have rigid parts, the rule-based algorithms like CAD matching and geometric matching and edge matching are very suitable for those. You have levers that you can pull to adjust them. You're just kind of tuning it into a rigid object that doesn't change a whole lot. The use of deep learning there, you're just kind of making yourself a headache, because deep learning can become a black box in some instances, and it doesn't always isn't always the best solution out there when you can have more control on the plant floor, on the user engineering side, if you can just pull some levers to change a rule-based algorithm. Where we see deep learning being very capable and very useful is more in that logistics and consumer goods side of the applications, where you're getting into depalletizing or bin picking, where you have flexible or deforming objects. So a lot of, you can get into depalletizing of boxes, you can get into bin picking of, say, granola bars. We've done some stuff with potato chip bags, right? Things like that, where you get into very deformed objects that would be very difficult for a rule-based algorithm to understand. That's where deep learning fits very well, and it works extremely well to solve the applications. So when you look at deep learning, you have two different functions. You have the 2D function, which is where the classification and segmentation happens. Classification means that we can actually, in this algorithm, tell you what we're looking at. So if you have, 3 different types of potato chip bags, different colors, different graphics, whatever it is, we can actually train the system to understand all of those and tell you which one's being picked. If you had a bin full of, all 3 of them, or if you just had a conveyor or anything like that. Then the system, in addition to classifying, will also segment on the 2D image. It will actually determine, what's my object of interest in this 2D image. From there, it will then move forward into the 3D image and extrapolate that segmentation, the 2D image, into the 3D point cloud to create your localization. And so from there, you end up with things that you see here. And that all comes from the annotation step, right? In that 2D image, you're going to train it, you're going to annotate. And that's going to create that training so the system can create that segmentation, and later on that plane development in the 3D point cloud. So you can see different types of items here. You can get into overlapped items in the bin. You can get into mixed items in the bin with deep learning. Or you can just get into items that are very tightly packed that become very difficult for rule-based algorithms to understand. Both of those are shown here. And so how we do annotation, again, this is like the magic sauce, right, of how you annotate these images effectively, how you get into not having to need 10,000 images. That goes into Deep Annotate. Deep Annotate is our platform for training of the deep learning algorithm. This is actually something that's available to customers. It's available to Hartfiel, to SICK. Everyone can use it. It is something that needs to be paid for, though, when using it. And what we've done in our deep learning is we have created what we call a transfer learning network. We have taken open source data and created a foundational layer in our network of millions of images. So the network natively understands millions of different things from a warehouse and a consumer goods setting. And then we use that data to bias it towards your application based on the images that you're providing with annotations. Generally for us, that means we only need about 50 to 100 images. We're just biasing this network. We're not creating a whole new one. So you don't need 10,000 images. We generally need 50 to 100, and you're just going to have to do some light annotation because this tool actually does a lot of the automatic annotations as well. You just kind of have to touch them up. It does them based on that existing network. And then it goes ahead and does training. And because it's just a bias training, it's not a complete training. it generally takes about 5 to 10 minutes to train. So generally with this tool, we're able to go from not having a neural network to having a very good neural network in about 30 minutes to an hour. And then you'll get some edge cases and you'll probably make 2 or 3 iterations before you have a network that's probably going to solve the majority of your application. It's very, very quick, very easy for a deep learning system based compared to much of the technology that's out there. So that was deep learning. Now, hand-eye alignment, this is the next step in PLB. This is where you can actually get into your robot, right? We're no longer just playing with vision, trying to locate things. Hand-eye alignment is where we take PLB and we're teaching the robot's coordinate system to it. And so for different types of applications, different types of needs, we have different types of processes. So in the different applications, you might have a robot mounted camera. That's what you see up here at the top right, that's moving. This is where we mount the camera to the robot. We have a fiducial in the workspace, and we're going to move the camera around to view this fiducial in different areas. And we're going to report the flange point every time we take an image. That allows us to understand where the robot is, where the camera is, where the fiducial is, and figure out all that data to figure out where the camera is via the flange and where the robot's base is relative to our points. When we're doing a fixed mounted camera, the bottom right's what you're going to see, where we have a cone or a sphere attached to the robot, and we're showing that to the camera. And at each point, we're going to report the tip of that cone or the center of the sphere to the camera. And so then we have the knowledge of where that cone or sphere is in the camera's coordinate system, where it is in the robot's coordinate system, and we can create a transformation. And then the last way of doing this is the grid that you see at the bottom left. This is mainly for depalletizing, where you can just get into show the camera a grid, touch off on a few different points with the robot, and then we can again understand where the robot's coordinate system is relative to the camera. The main thing again is that we're going to learn the coordinate system of the robot in the camera, so that when we report positions to the robot, those positions are in the robot's coordinate system. There's no post-processing on the robot's end after this hand-eye alignment process. And so those positions that we report, you're going to get 5 different positions. They will be a entry point above the bin, a approach point, a pick point, a clear point, and then an exit point back above the bin. We collision detect all of these so that we make sure that you're not going to collide into anything on the way in and out of the bin, and then you're good to go. You just run your robot through that point sequence, and then it's able to pick and then place the part based on the robot program. So we'll go ahead and next slide. So there are different, as I've mentioned, there are different system configurations here where you get into different cameras as your base and then different algorithms. So we have different tiers of pricing. Each camera has its own base pricing, and then based on top of that is the different algorithms. So your edge algorithm is kind of our lowest base model for the PP version. The PL version gets into the geometric and deep learning algorithms, and then the full version is when you have CAD matching and everything else available to you. So these all go to different price points, which allows us, again, to mold the system, mold the pricing into the needs of the application. So some key applications here. I'm going to go through a couple before we go to questions. So I'm going to skip ahead in this video a little bit. This first one here that you see is going to be depalletizing. This is where we're coming in, we're picking boxes, which can be mixed. It could be a mixed pallet, it could be a homogeneous pallet, tightly packed, or a complete mess. Either one works, and we're using the deep learning algorithm to be able to effectively pick these. There's different features in PLB that are built for this. So you have your layer-based sorting, for instance, that allows you to pick in from the corner, make sure you're picking these effectively rather than just picking, the highest Z, and it could be out in the middle. The system does do a layer-based sorting, which allows you to choose that I'm going to come in from this corner and I'm going to pick this, row, this column first before I go to the rest of them. You get into other features like collision avoidance that allow you not to run into any of the other boxes, among other things here. Other applications, we get into high accuracy bin picking. This is where we use CAD matching in one of the higher end imagers to be able to pick something like, maybe I'm gonna press play here, to pick something like a automotive stamping. Again, there are key features within the software developed specifically for this application. So for instance, we have a define pick pose command where if you have something like the bottom right image where you have stacked stampings, the robot will come in and, the camera takes an image, it localizes, and then you can jog your robot to the point that you want to pick at. And you can actually report that point back to PLB. So that way you're not having to graphically try to tune in this point. You're actually going to it with the robot and reporting where it should be, and PLB adopts that position for the job. That's actually really nice. It makes your setup much cleaner, much easier, faster, and more accurate. Instead of having, again, to tune in the job very basically. So again, there's a lot of tailored features for these different applications we've been able to focus on over the years. Another one here is piece picking and order commissioning. This is, again, a deep learning application, but this one gets into a different type of camera. Again, this is more of a high accuracy camera where we're looking at maybe some clear bags, some clear objects, and we're needing to use deep learning to segment those and pick those effectively. It could be mixed skew totes, it could be homogeneous skew totes, really anything, but the idea with order commissioning is that you're picking something to fill an order. You have an order come in for, 10 of these, 5 of those, 2 of another, and you have 3 totes in front of you. You need to fill a little bit of each into the outgoing box. That's what this is here that you're seeing. Last application here is tire depalletizing. And so this is something that is a very nice application. It's a little niche, right? It's something that is very unique. It's specific to tires, but it's very effective. We have a really nice tire algorithm that you really just put in a range of the tire sizes you're looking for, and the system will automatically go out and figure out, hey, this is a tire, you can pick this, here's the size, do you want to pick it? We've done a lot of tire depalletizing and a lot of tire bin picking applications with this. Really effective, really fast, generally will process within under a second, and has really good accuracy. In addition, PLB can also do gantry-based work. So if you do like a 4-axis or a 3-axis gantry, it is capable of doing that. You can see that in the upper right-hand corner here. We do get into that a bit in tire applications. So again, just another application that we're able to solve effectively. There are many other applications that PLB is able to solve, right? So they do not limit, the understanding to those past 4. Those are just 4 unique, cool applications. You can see here, brake disc depalletizing, like you see on this particular video. Formed dunnage, cell dunnage picking, where you have items that are being held in a tote or a pallet via some type of dunnage. Index conveyor picking, casting depalletizing, green tire picking, billet picking, tote depalletizing. All of those are things we've done, and there's much more that has been done with PLB. It really is a platform for 3D guidance that's able to mold itself into a lot of different needs of the industry. In addition, we keep working on different ways of using it. So you can see here I have an asterisk on moving conveyor picking. That's something we're actually testing in our lab in Detroit, Michigan right now, is how we can use PLB to do moving conveyor applications, where maybe you have we've seen applications where you have food items that are up against each other, or they're overlapped, or anything like that on a slow moving conveyor. We've had some initial success using PLB to do that with deep learning and some of the faster 3D cameras. In addition to that, you might have index conveyors that have layered items, things like that. So there's a lot of different applications we're still working on figuring out the limitations of the software. So this is always going to be an evolving thing. So if you have something new that has not been done with PLB, let's talk about it, because we might be able to do it still. We just haven't tried, possibly. So last thing here, there is PLB literature that's being given as a handout. And that's something that you can review with some of the key applications that I just mentioned. That's all I have.
Awesome. I swear, Nick, the more I see PLB applications, some of them are just black magic, what you guys are able to do there. Yeah. So if you guys have any questions, feel free to chat them in now. We'll probably hang out until about that 10:55 mark or so. So feel free to ask any questions. We'll just hang out until then. Thank you, everyone, for your time. All right, it is 10:55, so we will head out. If you guys do have any questions, feel free to reach out to sales@hartfiel.com or work with your local account manager. They'd be more than happy to get you involved. We'd be happy to get any of these products out to you guys, do some testing. But thank you very much for your time on a Friday.